Okay, YouTube, this is my first video in a series that I'm doing over sum and difference formulas. And sum and difference formulas, you can see these are listed up here on the left, but we say that we have three of them we often refer to for sine, cosine, and tangent functions. And I'm going to go ahead and start by kind of illustrating not so much how they work as much as why we use them in the first place. But we say that the sum and difference formulas are useful for two things. First of all, they're useful when verifying trig identities. So often it is beneficial to take something that is a sum or a difference of two angles, and we're taking the sine of it, and rewrite it in this form in order to verify a trig identity. And another reason why we use these is because sometimes we're asked to find exact values, okay, not just in a calculator values, but maybe like the exact value of the sine of 15 degrees. And what it does is it behooves us to rewrite this as possibly like 45 minus 30 degrees. Thusly, where this would be like our u and this would be our v, and this is a difference in this particular case. But what that allows us to do is go rewrite this in terms of u and v, where now we're using 45 and 30, which are, if you recognize here, two very common angles that we're used to using on the unit circle here. We could even say, what is the sine of, I suppose, let's see here, 120 plus another 45 is 165, something like this here. I don't know what the sine of 165 is, but we could necessarily rewrite it as the sine of 120 degrees plus another 45 degrees, where 120 would be our u and v would be our 45. And again, these are angles. This 120, we already know the sine and cosine of 120, and we already know the sine and cosine of 45. But what this allows us to do is basically take interesting angles like this and rewrite it as a sum or a difference of angles that we're already, familiar with or have available to us on the unit circle. So let's go ahead and take a look at a couple of examples, starting with the sine of pi 12ths here. Now, the first thing I want to say about pi 12ths is this. It's obviously in radians. And so when you talk about how is it that we could compose two angles, add or subtract two angles to make a pi 12th angle, it's a little bit more difficult to do in your head than if you were to be dealing with degrees in the first place. So if you're ever dealing with a radian measurement here, not that there's anything wrong with me saying that this is technically a pi 4th, which is a 45, minus a pi 3rds, which is a 30-degree angle, but it would make more sense, at least for now, to interpret this as a degree measurement. So what I'm going to do is I'm going to take this times 180 degrees over pi, and we'll convert this into degrees so we can work with this mentally, okay? And 12 and 180 here, we see 12 goes into itself once, 12 goes into 180. We can check this on a calculator. I think it's 15 times. We say 180 divided by 12. And we do indeed get 15, so this is 15 degrees. So I'm going to temporarily rewrite this as the sine of 15 degrees. And the idea here is going to be this: how could I use two angles that I'm already familiar with on the unit circle and either add or subtract them in order to make a 15? So we say, well, I don't know, like a 45 and a 30. If I were to take 45 minus 30, these are two angles that I already know, and that would compose a 15 here. So what we're going to do is we're going to rewrite this original sine of pi 12 statement. We're going to rewrite this sine of pi 12. And we should be doing this in radians. I only did it in degrees first of all so that we could think of this. We'd say 45 degrees minus 30 degrees. Now that we have the two angles that are on the unit circle that we could subtract, say in this case, to get this, we're going to rewrite this as the sine of those two angles in this difference, but in radians. So we say sine of pi 4th minus sine of pi 6th. Okay? So, that's a 6, not a 3 here. But we say, okay, so now, using our sum and difference formulas, notice that I'm taking the sign of a difference. And that refers to this top formula up here. We're talking about sines, and I've also listed this down here. But the peculiarities of this formula say that sine of u plus v, or sine of u minus v, is sine u cosine v, plus or minus sine v cosine u. So we just need to know what our u and v are here. And I'm actually going to list this out here. We say our u is like this pi 4th right here. And our v, ignore the difference here. It's not a negative v. It's just that v is pi 6th. And we're subtracting that v right there. Okay, so now that we have u and v, we're going to rewrite this. Now you notice when I rewrite this, this first sign here was a plus minus, and this was a plus minus. What this means is whatever sign was in here, this is going to match this. Now, we're not using cosine in this video, but I do want to point this out about these sum and difference formulas. If we wrote plus minus here, you notice that for a cosine formula, it's minus plus. And what this really means is that's going to be the opposite of the initial sign. Try to write a T there, S-I-G-N, sine. Okay, and the same thing down here for tangent. This is plus minus, the top is plus minus, but the bottom is minus plus. It'll be the opposite of the top and whatever's over here. So let's go ahead and rewrite this as what we can do here is, an expanded expression. So we say sine u cosine v. So we get sine of u cosine of v. And this will be minus, since this was minus, and our formula indicates we should stay the same. And this is also sine cosine. So we have sine v cosine u. And so what we're going to do is we're just going to plug these in. We say u and v. So we say pi fourths, pi sixth. And then we have pi sixth, pi fourths, because we go v and u over here. So now that we have this as an expanded expression, what we can do is we can get an exact value for this. That is to say, we should know the sine values at these angles, but we can go refer to this unit circle. We say sine of pi fourths, of course, is root 2 over 2, and cosine of pi sixth, if we look at pi 6 here, is root 3 over 2. So we get this. We get root 2 over 2, and this is root 3 over 2, and this is all minus now the sine of pi sixth. Well, if the cosine of pi sixth is root 3 over 2, this will be a half. But again, we can go look at this. We say pi sixth, this value here is a half. And then the cosine of pi fourths is, of course, root 2 over 2. That's an isosceles triangle. So we're going to multiply this out and combine like terms, but we'll talk about what kind of a value we get here. So root 2 times root 3 is root 6, and 2 times 2 is 4. This is minus 1 times root 2, which is root 2. This is over 2 times 2, which is 4. So I'm going to write this as one giant fraction here. It's not very giant, but we say this right here. That I'm going to put a box around and we're going to label this. We call this an exact value, okay? So the benefit to doing things this way, and I can talk about this exact value, what if we were to evaluate this? So we say 6, the square root of that, so we take the square root of that, okay, minus, in parentheses, we say 2 square root, end parenthesis, equals. So here's our numerator, and if we divide this by 4, we just got the sine of this initial value, which was pi 12ths. So now, what I want to do is this. I'm going to pop my calculator into radians mode here. We've got about 0.2588. If we were to do now the, let's see, pi divided by 12 equals, and then take the sine of this, you recognize this number. So the idea here is this. We could have done this in a calculator, but this is a, an approximate value, whereas we can get exact values using the sum and difference formula. So again, let's go ahead and take a look at, say, the sine of 75 degrees up here. We say, all right, well, sine of 75, what I'd really rather do is I'd really rather write this as a sum or a difference of two angles that I'm very familiar with. And so, I don't know, we'll have to pick a sum or a difference, but we say, what two angles could I use on the outside of the unit circle that would either add up or subtract off to be a 75? And I noticed that I could use like a 45 plus a 30 here. But let's see, are there any other ways I could have made a 75-degree angle? And one thing I'll point out to you is we could actually use a difference. We could take 120 degrees, right here, 120, we know its values, and subtract off 45, for which we know its values. 120 minus 40 is 80, minus 5 more is 75. So we could either do this as a 40-degree angle plus a 35-degree angle, or we could do this as the difference of 120 degrees and 45 degrees. What I'm here to tell you is there are multiple different combinations you could use here. I think that this first one here is probably the easiest one to do. So I say in that first case, we say that's a, 40 plus a 35. You know I mean 30 plus a 45. I apologize there. 30 plus a 45. It's early this morning, so we say U is like 30 degrees, and B is our 45-degree angle. We know the values of sine and cosine of 30 and 45. So we're going to rewrite this using our sum and difference formula for sine. So we have sine cosine, plus or minus. So this is a plus, this is a plus, and we say sine cosine. And we're just going to drop in our angles here where we say it first went U, then V, and then for our sine formula at least it goes V, then U. So 45 and 30. And so this is where knowing these things is helpful. It comes in handy. We say sine of 30 is a half. Cosine of 45 is root 2 over 2. Again, we could go refer to the unit circle just to see these things. These are common values. So sine of 30 right here is a half. Cosine of 45 is root 2 over 2. Sine of 45 is going to be root 2 over 2. And cosine of 30 is going to be this root 3 over 2. So we have plus root 2 halves. And this would be root 3 halves. And we'll go ahead and get an exact value for this here. So we root 2 over 4 plus root 6 over 4. And we get root 2 plus root 6 over 4. So the sine of 75 degrees is exactly equal to this value right here. In the next video, we'll take a look at some cosines, and after that, we'll look at some tangents. Cheers.